Morning.
Morning.
Good lesson today. Start proving that. Maybe I need to make that bigger for you. Some really good problems today. Some of the best problems of the year. Folks, we are almost done with this course. My goodness. This is the most difficult lesson we have left. The next two sections are much easier than this. I'm looking at them right now. There will be auxiliary segments in these proofs. You're going to have to figure out what auxiliary segment you're going to want to use. That's what makes it so difficult. Trying to find this one problem that was fun, and I can't find it. Darn. Oh well, we have good problems in here. Anybody figure out a proof for this? For these? Any one of them? No? You guys still there?
I'm still here.
Still here?
Still here.
Okay. Anybody working on it? Or just hanging out?
I'm trying to work on it.
Did you get an auxiliary, just one at a time on the first case? Did you get a, did you draw an auxiliary segment somewhere?
Yes, I did.
Okay. And when you draw an auxiliary segment, try to capture X and Y. Try to capture those arcs in there. If that makes sense at all. Oh, time to start. All right, good morning, everybody. Oh, Mr. Lauchu is calling me. Here, I'm gonna, while he's calling, I'm gonna give you the auxiliary segment. There it is. Hello there. Just started my Zoom lesson. Hello? Hey. Hi. Hey guys, I just started my Zoom lesson for my geometry. I'm live right now, actually. Did you guys want to say hello to the students? I have a gap in between this class of half an hour between this class and the pre-algebra class. And then the pre-algebra class, oh, this one goes from 8:30 to 9:30. And then at 10 o'clock, I start the pre-algebra. Okay, you got it. Bye-bye. All right, that was Mr. Lauchu. Okay, you guys see this here? Let me shrink this down just a tad, a little bit more. More. I guess we'll just go back down to 140. There we go. Okay, you guys see this auxiliary segment? It's okay, so let's draw what's going on here.
We need to change that, I think, because it's not going through the center.
Doesn't need to go through the center. So the way you're trying to do it through the center is I don't know if you're going to be able to do it that way. So here we go. I'll get it up here. So you have, what do we have? We have 2 secants is our first case. from this point through the circle, and from the same point through the circle. And what we're trying to say is that when two secants meet outside the circle, yesterday we finished with when they meet inside the circle, these two arcs that are intercepted, and we had them in red and blue. So this one here, okay, and this one here in blue. And then we talked about what do we know about this angle? Well, when this point was inside the circle somewhere, we knew that this angle was the average of the red and the blue arcs. It was half the sum is what we're going to say. But now we're trying to say that when that point, when these two lines that meet outside the circle, then that angle is going to be half the difference of the two arcs. All right, and we're going to have to show that. So here we have A, and we have B, and we have the C is the meeting point, and we have D coming around here, and we have E. And so you can see an auxiliary segment drawn. To there. Okay, and when you draw that auxiliary segment, it does not have to go through the center. All right, so what we have now is a triangle with an exterior angle, and that's what's going to be the trick here. You have this triangle that has angle 1 here, okay? We can call this angle 2 and this angle 3. All right, so everybody see that triangle right here. Angle 2, angle 1, angle 3. Now, we know by the triangle exterior angle theorem that the measure of angle 3 is equal to the sum of the measure of angle 1 and the measure of angle 2. Any questions about that so far? Something that we know about angle 3 also is that the measure of angle 3 is an inscribed angle with the red arc, right? The measure of angle 3 is 1/2 the measure of arc AE. And now look at the angle 2. That's where the blue arc is. So the measure of angle 2 is half the blue arc, half the measure of arc BD. Any questions about that so far? No? Okay, great. So now substitute. Oh, before you substitute, you can change the purple one to get a difference, right? Since we're going to solve for this angle is ACE. ACE. That's what we marked here, angle 1. Solve for angle 1 first if you want. You don't have to, but you can. Subtract the measure of angle 2 on both sides. So the measure of angle 1 is equal to the measure of angle 3 minus, there's your difference, the measure of angle 2. Okay, so I went from purple to blue there. Now substitute, and I'll do that down here. The measure of angle 1 is equal to, all right, so the measure of angle 3 is half the measure of arc AE minus half, I'm going to substitute for 2, half the measure of arc BD. And then you just factor out the 1/2. Okay, so if I factor out the 1/2, I get measure of arc AE minus measure of arc BD. Oops. So the measure of angle 1 is equal to half the difference of the intercepted arcs, the red and the blue. Questions about that?
Actually,
You could
I was
also
wondering about the auxiliary segments.
The auxiliary
Auxiliary.
segment, this red dotted one here, this green one here was auxiliary. So this is a case, what you're going to have to do is recognize when two secants meet outside the circle, that angle is half the difference of these two intercepted.
Oh, okay, I get it. I get
That's what you're gonna have to spot.
And when the inside, when they meet inside, then
Hold on one
it's
second. This is the proof of that. But that just because you understand what I just did here doesn't mean you're going to spot this when we start to apply it. Okay? All right, go ahead. Whatever comment you wanted to do.
the when the secants meet inside, it's half the sum of the arcs.
When it meets inside, it's half the sum. That was the theorem. That was the part of the theorem that we ended with yesterday.
Okay.
Mr. Rosenthal,
Mm-hmm.
how did you get from measure of angle 2 is equal to 1/2 measure of BD to measure of angle 1 is equal to measure of angle 3 minus measure of angle 2?
Purple to blue?
Oh, okay.
Subtract the measure of angle 2 on both
I
sides.
just subtracted the measure of angle 2 on both sides.
Okay.
Anybody else? Questions before we move on? When is the chapter 11 retake? We say that a lot of students say it as if there is a retake, like that. It's not, it doesn't quite work that way. I don't have a retake at all to give you yet, and it's going to take me time to work that out. All right. So I don't have that yet. I'm working on that. That's the answer to that. So I don't know when. That's the answer is I don't know. So hopefully soon. And then there's no rush. We have months to go. There's no state testing, so there's plenty of time to do that. Right now, I recommend you focus on chapter 12. Maybe I'll do all retakes after we're done with chapter 12 to help those students focus on chapter 12 and not split your attention between two different things. Okay? All right. Any questions about case 1? So what would another case be?
On the circle, but that would be an inscribed angle.
What would, well, if that was already on then we already know that angle's half that one arc.
Yeah.
So I'm talking about two lines meeting inside the circle. It could never be a tangent, right? Tangents cannot go inside of a circle. All right? Secants can go inside of a circle, right? So we had that. See, two secants or chords meeting inside the circle, but tangents could never end up in here. Okay, so that was that part 1 was that. Part 2 has 3 cases though. All right, this is where points are outside the circle. All right, so now you can have tangents. So you can have two secants, that's our first case that we just did here, that meet outside the circle. What would another case be?
A secant and a tangent, and then two tangents.
There we go. When a secant and a tangent meet, the same thing is true. That measure angle B there is still going to be half the difference of this arc and this arc. Why those two arcs? Those are the arcs that are intercepted by the tangent and the secant. Okay, so go ahead and see, they give you this auxiliary segment here. I'm going to give you 2 minutes to get a head start on the proof while I draw this on the board. Go. Try to prove this.
Wait, what does that say? Measure of B.
Measure
I can't really read it.
half the difference of the intercepted arcs. Arc
The
A
equal sign?
equal here? Yeah.
Okay.
And now I can make this a little bit bigger. I can jump this back up to
Wait, it says
185.
construct AD.
Well,
Yes, that's the auxiliary segment that we need for this case.
that's this auxiliary segment.
Oh, I thought I was going to ask us to construct.
Use the same thing, the triangle exterior angles theorem. You're going to use that again. So now you should be able to do this with that theorem. Okay. Let's see. So now we have a point out here, B, that's going to be tangent to the circle here. And there's going to be a secant here. B. A. D. C. Circle O. David's favorite.
why circle O? I hate that when it's in a paragraph proof. It's like the circle symbol and then the O. I'm like, what? Ew.
There's your, okay, so I have that auxiliary segment, which makes a triangle. So I want you to focus. There's angle 1. Okay, let's do angle 2, this one, and angle 3, that one. Let's mark our intercepted arcs. I'll do the bigger one in red. Smaller one in blue. Hopefully the color coding makes this a little bit easier.
And that theorem still holds true when it's tangent instead of
Well, that's what we're
across
gonna.
the circle.
That's what we're gonna prove.
No, but the other theorem, the one that says it's half the intercepted arc, it still holds true with the tangent.
What's, oh, this one here, the blue one. The numbered angle 2, you mean?
Yeah.
Yeah, angle 2 is the same as an inscribed angle. That's
Yeah.
that's the one. Angle 2 is the one students forget. Angle 2 is half the blue arc. That's what you guys have to remember. That's the one that students forget. Angle 2 is half the blue arc, arc AD. Okay, it's been 3 minutes. Do you guys need more time?
No.
Only answer if the answer is yes. Do you need more time to try to do this yourself? Okay, no response. Okay, let's do it. All right, so let's start with the triangle angle, the triangle exterior angles theorem says the measure of angle 3 is equal to the sum of the measure of angle 1 plus the measure of angle 2. Let's solve for the measure of angle 1 again. The measure of angle 1 is equal to the measure of angle 3 minus the measure of angle 2. Subtraction property of equality. Okay, so from there now we can go our different direction here. Let's go and say something about the red arc and the blue arc. So angle, I didn't complete this arc. There. Angle 3 here is an inscribed angle that is half arc AC. So the measure of angle 3 is equal to 1/2 the measure of arc AC, the red arc. That is the inscribed angle. Angle 2 is an angle made from a chord and a tangent, which is like an inscribed angle, right? So that angle 2 is half the blue arc. And this is the one that students don't see. So you should, if you have questions about that, we can go back to the slide where we showed that. And there's no pun intended there because we showed that with a slide by sliding point B around till it got to land on that point of tangency. So, okay, so the measure of angle 2 is half the measure of arc AD. All right, and so this one's gonna go just like the one we already did. You're gonna substitute 3 and 2 up here, 3 and 2. Okay, so the measure of angle 1 is equal to half the measure of arc AC, substituting this in for 3 here, substituting this in for 2 here, minus 1/2 the measure of arc AD. Factor out the 1/2, and it's the difference of the arcs, half the difference of the arcs.
In the third case,
Hold on, let's just stick with the second case. Any questions about case 2? I did this one a little cleaner than the last one. I moved my picture over to the side, gave myself room to go straight down. Questions about this? I'm not asking you to prove these on the test. I'm asking you to understand and follow the proof and the logic. Okay?
So it says measure of arc AD on the last part, right?
Yes, right here, yes.
Okay.
All right, so really what you're going to want to come away with on this, having gone through the logic and following what I didn't do anything too difficult here. What you're going to want to be able to do with this is spot these things. You want to spot that angle 2 is half the blue. You want to spot that angle 1 has to be half the difference of red and blue, those arcs. All right, you want to be able to apply. You want to be able to apply these theorems. All right, and it's easy to forget these things. All right, we're going to move on to case 3. What would case 3 be? So we had a secant and a
Two
secant.
tangents.
Okay, so you're saying 2 tangents it would be? Let's see.
Yeah.
And we already discovered something about 2 tangents, and we talked about it yesterday.
They're congruent.
If we drew a radius to point A and a radius to point C, you would have a quadrilateral, right? Like that. And these would be right angles, right? And in all quadrilaterals, the sum of the interior angles is what, everybody?
360.
360. And when you draw these radii out to A and C, you've already taken up 180 of that. That leaves you 180 to be distributed amongst this central angle and B. But the central angle is congruent, or it has the same measure as the arc. Okay? So if these are supplementary because they add up to 180, then this angle, it will be supplementary to the arc here. So that's something we know. Here's something else we know. We know that it also follows this, that it's half the difference of this arc and that arc. Okay? So we can show that. It's not as applicable. It's much easier to just say, oh, if I just know this arc, that's supplementary to that arc. That's faster than what we're going to show here. Okay?
If the auxiliary segment AC goes through the center, then angle B
Could it?
what was it?
Is there such a point where you could, then these would be parallel lines and they would never meet, they would never touch.
Yeah.
You can't do that. All right, here we go. We have point B, tangent here.
Yeah, the measure of angle B would be 0.
Okay, and then let's do another tangent. Okay, and then circle O, David's favorite. D, point of tangency A, B, C. We have auxiliary segment, AC, makes a triangle. The triangle we want to discuss is going to be this one here. There's angle 1, that's what we want to find. Exterior angle is going to be either here or here. It won't matter because they're both tangents. Not one tangent is more important than the other, so you pick one. So this can be the exterior angle, and this can be the other remote interior angle. Now, the 2 is a chord and a tangent. So this arc is related to angle 2. It's double angle 2. And on this side, angle 3 is also made out of that same chord, but with this tangent, and that spells out this arc.
It's the entire circle.
Well, yeah, when you put them together, red and blue make up the entire circle, yes. All right. Which is why it's going to show you that they're supplementary. Watch what happens here. Okay, so we'll set this one up. The exterior angle 3 is equal to the sum of 1 and 2. And we'll solve for 1 by subtracting. Same deal.
It's the exact same thing every time.
It is, and I want you to see that. Okay, next, what we're going to do is we're going to say what the measure of angle, what that is. The measure of angle 3 is half the red arc ADC. Look how they put a D there so that you can call the major arc what it is instead of not knowing if it's the blue or the red. That's why they put that extra point there. If
Measure
you,
of angle 3 is 1/2 arc AC. Measure of angle 2 is 1/2
hold on, David.
arc AC.
You can put stuff in the chat if you would like.
David, can you let other people get it first?
Yeah, exactly.
You kind of just keep blurting everything out before you see.
Yeah, don't blurt it out.
I'm not saying an answer.
Okay, there's the measure of angle 3 is half of the red arc. The measure of angle 2 is half of the blue arc. And that's the minor arc AC versus the major arc ADC. And those are ready to now plug in. Okay, so the measure of angle 1 is equal to, so here, the measure of angle 3, we will substitute half the measure of ADC minus, now the measure of angle 2, we'll plug in half the measure of minor arc AC. We will factor out a 1/2. And we have what this says, but I want to go further than that. Okay? I would like to go further than that. Let's see. How do we go further than that? I want to show that the measure of angle 1 is supplementary. I want to show that it's supplementary to minor arc AC. I want to show that the measure of angle 1 plus the measure of arc AC is equal to 180. How might I do that? I know that if I add the arcs, the measure of arc ADC plus the minor arc AC, I know that that's 360 degrees because the red and the blue take up the whole circle. Okay, so
Look at on tangent BC, angle 3, and since it's base angles, angle 2 are supplementary, and then you could put that in that 1/2 measure of angle.
wait. Why are angle 3 and 2 supplementary?
The congruent.
Oh, you're saying I can take wait, if I take half, okay, watch this. Take half of everything here. Divide by 2 on both sides. What do you get?
180 equals 1/2 ADC plus 1.
Half of this, 1/2 of that, and this becomes 180. So now I know half of these arcs, when you add them, you get 180. I don't know if that's tagging on to what Zig was saying.
Measure of angle 1.
It is because the tangent BC is a straight line, and because the base angles theorem, and because the two sides of the two tangents are congruent, angle 2 is also the same on the tangent BC. Touching, well, I should say angle ACB is angle 2 as well. Is congruent or equal to angle 2.
Oh yeah, because these are the same because they're both tangents, then these
Yes.
angles are congruent. Okay, yes, and
And
they intercept the same
then-
blue arc.
And then angle 3 and angle 4 are supplementary by definition. I don't
Both
know
along
if
the
they're
straight angle, yes.
Yeah.
Okay.
Wait, how about
but they
this?
would be
Draw.
supplementary.
So 2
Draw-
and 3 are supplementary. Good.
How about
Okay,
this?
okay, that's fine. You're taking a different route. How can I get from this, what I have here and here, to get that they're supplementary?
You don't need that to get that they're supplementary.
No, we just did it another way. But
Well,
can
well,
I?
the other one aren't you trying to get that angle 1 is supplementary to arc AC?
Well, we did it by saying if you have this and this, these are right angles, right? Okay, so X and Y must add up to 180 because of that. We got that part. But I wanted to know, can I get to it some other way with what I have here? We have a lot to do. You can try that at home and work with that and play around with that, but we have more that I want to get to that's interesting. So let's move on to the next example. Next idea. So we're done with that idea now. Now, well, we're not done with it. Let's see if you can apply it. Go ahead and find the value of X for these two. Go. So this is what you would be doing on a test. On a test, you would be using this to solve these problems.
Mr. Rosenthal,
Uh-huh.
does that say 56?
This is 46.
Oh, okay.
By the way, if that's X, and that's also X because those are vertical angles. So it doesn't matter which one what perspective you see it from. In this first one, you should have done right half the sum of the intercepted arcs.
Isn't it 46, not 40?
It's
46, sorry. Thank you. Okay, so this is 136. And then half of that is 68.
It's easier to just do 23 plus 45.
Yep, you can distribute the half and get 23 and 45. That's fine. It's easier for you. Any questions about the first one? So to me, this is fascinating because without the center, before we got to this idea, we wouldn't have been able to do this. We would not have known this relationship. We would have said, Mr. Rosenthal, we can't find that angle. We don't know anything about the angle. And now we do. And that those types of tools I really appreciate when you're trying to solve, let's say, engineering problems or other types of puzzles that we like to solve. That's going to be helpful. Any questions about the first one? I'm going to move on to the second one. Okay. Going once. Going twice.
Sold.
Okay. Second problem. This is case 2. They go right in the order that we learn them, so kind of makes it easy that way. And we assume that that's a tangent. And this is 20 degrees here. And we have X, this arc here. And then we have this one here is 95 degrees. And I set it, I don't care where X is. I don't care where X is. That angle that's formed is where I start. That angle is equal to half the difference.
95 minus X.
The bigger arc minus the smaller arc. We don't want to get a negative, right?
Multiplied by 2 on both sides.
Okay, David, let's not shout everything out. Because some people, David, it's hard to understand this, but other people are still absorbing what I'm saying and they're trying to soak this all in. And when you're saying ahead, their brain is now trying to rush through that absorption and they don't get to absorb it completely. So just remember that. Try to absorb that's happening when you're shouting out, okay? So slow it down a little bit. Any questions so far? That angle, we proved, has to be half the difference. Why half the difference? Because this point is outside the circle. When the point is outside the circle, it's different than when the intersection of two lines occurs inside the circle. That would be that angle is half the sum, both of these. Okay, all right. By the way, there could be a vertical partner over here if you crisscross those, but we're not, that's what these two are. You don't see it out here because we don't really need it. Okay, All right, so now multiply, like David said, by 2 on both sides to get this, and add x, subtract 40, x is 55 degrees. Okay? So if you were to think that that was a semicircle, you would have shown that it was not. Okay, any questions? All righty then. Okay, so now the fountain problem. I like this fountain problem. Okay, so here's a fountain.
The camera's angled down.
Hold on, I'm going to just show you this picture and then I'll move it down.
Okay.
So imagine you're the photographer, that somebody took this picture, and you can see that there's space, right? From the edge of the picture to the fountain. What if you wanted to take the picture so that the edge of the fountain on both sides went exactly to the edge, so that the edge of the picture was tangent to that circular fountain? So think about that idea as we come back up here and read this problem. Okay, you focus your camera on a fountain. Your camera is at the vertex of an angle formed by the tangents to the fountain. So here's a tangent, and here's a tangent. Notice you can't have it go tangent and capture a whole semicircle, because then you'd have parallel lines that never met. Okay?
Camera's angled down.
You estimate that this angle is 40 degrees. David, you're reading over me reading it out loud.
I'm not.
You estimate that this angle is 40 degrees, this angle formed. What is the measure in degrees of the arc, that's x here, of the circular basin of the fountain that will be in the photograph? And now we should know pretty quickly. That was our last.
Supplementary.
Our last case, we said it's half the difference, but that's the long way of doing the problem. We now know the short way of doing the problem is that this angle, formed by 2 tangents, I already heard David say it, is what to that arc? Supplementary. These two must be supplementary. So you can quickly gather here that x is 140 degrees. Okay? Now, follow up. To photograph a 160-degree arc of the basin, should you move towards, don't shout it out, put the answer in the chat. Should you move towards the fountain or away from the fountain to make the arc bigger? And then what angle should the tangents form to get a 160-degree arc? Okay, so you can put that answer. Do we move towards the fountain to increase the arc? To increase this arc to see more of the fountain? Do we go towards the fountain or away from the fountain? I'm looking at the chats to see what your answers are. Okay, I got an away, I got a towards to increase. Any, okay, smaller, away, 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 towards, away. I'm looking for more. Can you move a little up so we can see the diagram?
That's what I was talking about. The camera's angled down.
And move this up a little bit. Towards. Celine, you need me to move this down? The screen? No, okay. So do we move away or towards? Thanks. Oh, do we go towards the fountain or away from the fountain? Okay,
Way.
so imagine if I back this point up to here, what will happen to my angle? What happens to my angle? Does it become?
It'll get smaller.
Decreases.
The angle is going to decrease because as I move away and I'm still attached to those points, this angle is going to shrink down. So here, I can show it here. Watch this. So if I have, these points are fixed, right? If I back up, and I keep backing up, does that angle look like it's getting wider? What if it's really close? Look how wide the angle has to get. So as I get closer to the fountain, this angle is increasing, all right? But the angle, if these are supplementary, if this arch and this angle are connected, if that's x and this is 180 minus x, then they have an inverse relationship. Okay, so if I'm trying to make this bigger, that means this part has to get smaller. And we saw in order to make this angle smaller, I have to back up. All right? And that makes sense. If I move right up to the fountain, I put my eyes right up against the fountain, right? I'm basically staring at the wall. I really can't see around the fountain very well. As I start to back away, more of the fountain comes into view, doesn't it? You can imagine that. And I keep backing up and I can see more and more of the fountain actually, right? So what I want to do is I want to back up and I want to go from 140 to 160. So I need to add on 20 more to the arch, which means I have to take away 20 from my angle, okay? So I'm going to take away 20 from my original angle, so my angle
You have to have it, which means
20 degrees.
oh. So if you had a circle centered on that vertex where the camera is, with the radius being the distance from the camera to point A, then
Oh, to point A.
then if you move the camera to the edge of that to the back edge of that circle, it would then be 20 degrees.
If I move the camera and the camera is here, is the center of that circle that goes through those points. Okay, then what?
Yes. If you move, so the camera is originally at a point, like in the diagram on the
Almost like I'm dilating the circle bigger, you know.
No, that's not what I'm saying. If you have that diagram, like the diagram up on the screen, you have your camera a certain distance away from point A. You draw a circle centered at the camera with radius camera to A.
Which is what I have here.
Yeah, and then you draw the circle, and then if you move the camera to the back edge of that circle, you now have
There's two circles now. So which circle? The fountain or the circle that you
the
just
circle that I just drew. If you move it to the
draw what you're saying so people can follow. So here's point A from the drawing up there.
Yeah.
Okay. So this here goes to some center, which is the same as this. So these are radii of some imaginary circle.
Yes.
Okay. Now what are you saying to do with the circle?
We take the camera and we move it to the edge of that circle.
Camera. Okay. Because you're trying to double that distance, aren't you?
Well, have the angle, yeah.
Along what vector path? Should I come along this way? Or should I come along that way? Should I go straight back?
I think you should go straight back to get the same view.
Okay, so I go straight back, but they're all radii. Okay.
Yeah.
So you want me to double that radius, right? So it's this radius, and I'm doubling that down to here, which it's not drawn to scale, but okay. And so what does that do?
That puts the angle at 20 degrees. It halves the angle, putting the arc measure at 160.
Okay, so making the camera go here, because he's right. Why does it? This angle here, everybody, look at this. This is a central angle, right, to that circle. When you back it up to here and you make the angle, that's an inscribed angle, which is half of the central angle. So if this is 2x, this angle is x. So if this was 40 degrees, then he's saying to get to the 20 degrees, that's what you're doing.
That's the exact distance.
Yeah. Okay, very good. Excellent connection. That was really good. Oh, I didn't even have that in view. Very well done. Okay, let's move on. Oh, we have time. That's good. All right. So that was heavy. That was really heavy. Now that's only half of the heaviness of the weight.
Heavy, Doc.
Yeah, because now we're going to talk about the same thing, but instead of the angles, we're going to talk about what we know about the segments formed when we crisscross things. So
wonderful.
Why don't you guys take a 20-second brain break, actually, while I get this into view.
Hooray.
Too small. Shake out that brain. Because this is, you're going to need to absorb more data now. There we go.
Brain first, get some perspective.
All right. Take that time. Let me erase the board. Take your time. Look away from the screen. Rest your eyes for a second. Shake it out. Stretch. Okay. Get that. Erase everything that we just did out of your mind. Stop trying to cling on to it. Cling on? No, wait a minute. Okay. No Star Trek.
Okay. No.
Wow.
No.
Okay, sorry. Okay,
Fantastic.
so ready? Everybody cleared out everything? Okay, here we go. From a given point P inside. So now we're gonna go back to our first case where you have two secants or chords intersecting inside of the circle. You can draw two segments to a circle along infinitely many lines. And let me draw that out for you because that can get confusing. So pick any point anywhere. Right now we're starting with a point somewhere inside the circle. After that, we'll talk about what happens when you have the point outside. Take a random point, call it.
If the point's outside the circle,
David,
then
hold on.
your two segments of
Hold
the
on,
points
David.
won't be.
Hold on, David.
Oh,
Hold
yeah.
on. David, hold on. Okay. How many lines can I draw through point P?
Infinite.
Infinitely many. But each line I draw, how many places is it going to make contact or intersect the circle?
One.
One? So if I draw a line,
Two.
aren't I going to get a contact there and there?
I thought talking about the points.
How many, if I draw a line through P, a line, it will intersect, it must intersect, sometimes, always, or never intersect the circle at 2 points.
Sometimes.
Always. So we're going to call that, in the first case, A1, B1. In some other case, in a different color, we can call it A2 and B2. And maybe one more, doesn't matter. That's what Bob Ross always used to say, doesn't matter. Okay. Let's go this line.
A little accident.
A3, B3, doesn't matter. All right. So that has to happen always. When you draw a line through any point inside a circle, whether it's the center or not the center. Okay, well, what we are going to say is this. This is going to be our next theorem, and the topic of conversation now is going to be this. Let's start with my blue one that I did first. What we are going to say is that this segment here, let's say PA1, multiplied to its counterpart, to the circle on the other point, PB1, is constant along any line drawn through that point. So that's equal to
PA2 times PB2 times equals PA3 times PB3 equals PA4 times
got it out.
PB.
Put it in the chat. P times A2, so P times A2 here, times this one. This is going to be really helpful. We're going to solve some really cool problems with this. That is multiplied times PB2. PA2 is not P times A2. It's a segment, PA2. This segment times that segment. Purple times purple is equal to blue times blue, which is equal to red times red. What is red? PA3 times PB3. So that's this segment here. Everybody watch. This is why I like the gestures and you being able to see what I'm doing. Here times here. Okay? Okay? Any line you draw, wherever it makes contact with the circle, it's going to do that in 2 places. Always in 2 places. So because it does it in 2 places, you're going to have 2 different segments that you can multiply. You'll always be able to get the product of 2 segments. What 2 segments? It's from the point to the circle, from the point to the circle the other way. There's 2 ways to get from the point to the circle along a line, any given line. One way, the other way. If you're along the purple line, it's that way and that way. If it's along the blue line, it's that way times that way. But the product is always the same. Really weird, not intuitive. It does not seem like that and there's any particular reason why that would be the case. And so it's going to be our job to prove that. Any questions about what this says?
I have a comment.
Okay.
The purple line, the blue line, the red line. Why did you name them all after metro things?
After what?
The metro.
Oh, unintentional.
Wait, so Mr. Rosenthal, what does all of this mean?
It means that if I know, let's say that I know blue times blue is equal to purple times purple, and I know 3 out of the 4 of them, I can solve for the 4th one. It means that there's proportionality here. We're going to make proportions and solve for missing segment lengths. So for instance, Daniel, if I told you that this was 2 and that this was 10 in purple, and I told you in red that this was 4, and this segment, we don't know how long that is.
So you could do 2 times 10 is equal to 4 times x.
Correct. So x now you know is 5, don't you?
Yeah.
That's what this all means. It's an application that we now have with segment lengths. Remember, we just came off of a thick, dense material on angles. Now we're talking about segments, right? Formed by the same reason, by the way. Formed because of secants interacting with circles. Secants and tangents. Okay? All right. So, I'm running low on time. Okay, I don't know if I'm going to get to the engineering problem. Okay, so 1212 is the theorem that states this. All right. Case 1 is what we just did. We didn't prove it yet, but case 1 here is when they meet inside, you're going to get this being true, what we just said. When they meet outside, that's an interesting concept. How do we apply the same concept when the point is outside? What are we actually saying? And we're going to prove all this, but let's just find out what they're saying here, because this is maybe a little difficult to read. Okay, so the first case is when that point is inside the circle. What happens when the point's outside the circle?
The distance to the other side.
And you have, if you
times the distance to...
Let me ask you, how many lines are there possible through a point? Infinitely many. Okay, let's only consider lines that go through that point that also are secant to the circle, right? So that means necessarily that there will be how many points of contact?
A smaller infinity.
But, okay, that's fine. But how many points of intersection will there be by definition of a secant?
2.
1 and 2. Okay, so if this is still point P, this will be A1, this will be B1. If I do some other secant, okay, then this point is A2 and this point is B2. The same thing holds true, is that PA1 times PB1.
You use the PA1
now watch,
twice.
this is what's tricky. What's tricky is you are going through PA1 to get to B. There's overlap. It's blue, this little blue, it's purple times green. See that? There's overlap. The overlap is what's going to make this difficult. But that has to be, the way I think of it that makes it easy is you have to get from that point to the circle 2 ways. You must
No, it's stop.
Hold on. You must get from that point P to the circle along one line 2 ways. If you remember it that way, it's easy. Okay, the first way is from P, hit the A1. Boom, one way. The second way to intersect the circle along that secant line is to go from P all the way, the green one, all the way to B1. Those are the 2 that when you multiply are constant. Well, what does that mean that they're constant? Well, that means that if I go let's go
The same for a different line.
PA2 in pink has to multiply to along that same line, P all the way to B2. P to B2. Okay, that has to be constant. So from that point to the circle 2 ways along the same line has to be constant. So if I go from that point through another line that goes through the circle, another secant line, then that distance from here to the circle, even if it's way over here, even if it's off to the side, this distance times this entire distance is the same everywhere. Okay? And third case, any questions with the second case here? No? Okay. How would we apply this to the third case where one of them is a tangent? One of them is tangent from that point, and the other one is a secant. Well, for the secant, we have this segment times the purple segment, the whole thing, to there. Green times purple. And then you say, well, Mr. Rosenthal, you said that there's 2 ways. Well, there's only one way to touch the circle if it's tangent. So what do you do in a relay race when you have one less person? One person has to go twice. So it's blue times blue again. You have to go twice. You have to go from point P to the circle along the same line, but this is a tangent line. You have to go twice.
The PA1 squared equals PA1 times PA2.
Hold on, David, hold on. For the secant line, there's 2 places, here and here. So you can do the green segment times the purple segment because there's 2 locations. When there's only one location, it's got to be twice. So it's going to be T, if that's T, it's going to be T squared, right? And if green is A and purple is B, then it'll be, right? If green is A and purple is B, it's green times purple is equal to T times T.
Mr. Rosenthal, why is it y plus z multiplied by y instead of y multiplied by z? Just a question.
Oh, why that order?
No, why is it the sum of the 2 segments multiplied by one of them?
Well, look at this purple one. The purple is made up of this piece, which here is labeled Y, or here is labeled Y, right? That's the green piece, right? The purple piece is made up of Y plus Z, isn't it? What's purple? Purple is this segment plus this segment makes up the bigger segment, right?
Yes.
So Y plus Z is just talking about purple then. That's purple. Y plus Z is purple, Y is green. Y by itself is green. Here, I'll put it here.
Why is it purple by green? Why isn't it the segment that's only
Here, let me label
the
it.
circle?
Fine. It's
No,
it's P to the first segment
This
times P to the second point. Therefore, they overlap. It's just because the segments overlap.
I see. Never.
You see it, Zern? Purple is made of Y plus Z. Maybe I should have done this in purple.
Yeah.
Okay,
It's
green
because-
is only made out of Y. So then I can change this. T squared is equal to the green, which is just Y, times the purple.
P to the far point is Y plus Z.
Purple is Y plus Z. Okay? Now, we're going to prove this starting tomorrow. We didn't get through this lesson. Okay? That's fine. We're not in a rush. So I'm not going to go on at this point. I'm not going to start a proof and then, so we're going to have to prove all these things. All right? So tomorrow, we can get into the woods on this. All right? So any questions about any of this before we dismiss? Which line is purple? It's hard to tell. This one's purple.
I feel like this would be better represented with points.
With points?
Yeah, so that way you could say like PA for the bigger one, rather than Y plus Z. So
Well,
that
you're
way
gonna
we
have
can
to get
line.
used to it. You're gonna have to get used to it in y plus z, because that's how we're gonna put it on the test, where maybe
Y is a variable.
hold on, David, hold on. Where z and t, I'm gonna give you numbers and I'm gonna tell you to solve for y. See that? So I'm gonna give
Yeah,
you.
but just for representation purposes, just for like the introducing the basic concept.
We're
of y,
using
that would
Well,
we're
be-
using t, y, and z as variables. They hold a value of the length of the segment.
Yeah, you need to understand it both ways, okay? Draw this out. Look at the video again. When I first put this out, I still held on to the PA1, PB1, PA2, PB2. I did do that. So if you want to watch the video again and see it, you can. But you do need to understand it in both ways so that you can see, like David says, that these hold value, all right? So you should understand it both ways. All right, I'm going to dismiss everybody and see you tomorrow. And I'll have some office hours now if you want to stick around and ask questions.
Thank you, Mr.
Goodbye.
Goodbye.
Thank you,
Daniel.
Mr. Rosenthal.
No new homework.
Okay. See everybody at the tour. Biotech
Thank you,
tour.
Mr.
Oh yeah,
Rosenthal.
that's on the tour. Yes.
Goodbye.
Goodbye.
David
Rosenthal,
out.
have a good day. Thank you, Mr. Rosenthal. Have a good day. See you
You
tomorrow.
too. Thank you.
Bye.
Bye. Anybody else sticking around? Anybody have any questions before I end the session? Andrew, Mark, Nate, Natalie, Surin. Question, Andrew, Mark, Nate, Surin.
Mr. Rosenthal, I didn't catch Theorem 12-11 case case 2 number 1, I believe. No, the next one. After that. The one after. No, the one after. The one before in terms of order. Yeah, before that.
Got it. This one? This one?
Yes.
Okay, so this angle here, angle C here, is half the difference of these intercepted arcs, is what this is saying. Half the difference of these arcs.
This is the proof I didn't catch.
The proof here is the same as the next two cases, in which this exterior angle is equal to the sum of these two remote interior angles.
Oh, exterior.
Okay, now, this exterior angle is equal to the sum of these, right? So this angle, you can take this angle, the biggest angle, because it's equal to the sum of these two smaller angles, right? I could subtract this angle from the bigger angle, right? I can get this angle by just subtracting this one from that one because of that same exterior angles theorem. That's what's going to give me the subtraction. So right now I'm subtracting this angle minus this angle. But what is this angle equal to? It's equal to half of this arc because it's inscribed. And this angle is equal to half of this arc because it's inscribed. And that's where you get half of each of these arcs, which I factor out the 1/2. You see it?
Yes, thank you. I believe I'll be able to find it. Thank you, Mr. Rosenthal. Have a good day. See you tomorrow.
Okay, you got it. Mark, Nate, are you there? Respond in the chat or vocally. Nate, are you there? All right, gonna end the meeting. Goodbye.